Okay, so this problem of characterizing the curve that arises as the set of intersection of a plane with a cone. There is so this was one approach. This is one approach. There is yet another approach to the very same curve, and it is rather important. It's rather important to know them all. So the second approach is what I shall eventually call the second characterization. It goes as follows. Okay, so let's get right back to the original problem. Okay, so let's once again let's take a straight line, which you imagine as a vertical straight line, whatever vertical may mean. Okay, and let's take a point. Let's imagine that's the apex of your cone, and let's take a straight line that goes through that apex. Okay, and then so I shall eventually be rotating everything about this axis, and I will complete this thing into a cone. Okay, so that's my intention. So let me, okay, so whatever this thing, so this cone will initially, if you look at it from one side, it will look like this. All you will see is something like an infinite triangle. Okay, so that's what you see. Okay, so the plane, let's assume that the plane is somewhat like this. Okay, if you see it from the side. Okay, and then so I shall not initially take this inner circle, just as in the first case, but I shall take the X circle, which is going to be, as usual, a little difficult. No, it's these three tangent circles in the triangle. They are so damn difficult to get right. Okay, so it's possibly going to be something like this. Okay, right. So initially I've got this situation, right? And yeah, so that's what I see sideways. So I want you to, so the 2 points of tangency of this X circle, let me take them too, and let me join them. So eventually, when I have rotated everything, when I have rotated the whole thing, this X circle will become a sphere, and these 2 points will rotate into one another to get a circle, okay, in which this sphere touches the cone. So there will be a plane which carries that circle. So let's look at the thing sideways first, and let's assume that this plane and the original plane intersect one another. Of course, that's a straight line, and that straight line emanates from the blackboard, perpendicular to the blackboard, like this. But when we look at it sideways, all we see is just a point. Okay, so I'm looking at it, I'm just seeing, so there is a straight line coming out of here. Okay, right, so that's that. Right, now let's rotate the whole thing. So when we rotate the whole thing, okay, so let me start by, so to speak, okay, so that's the cone. Okay, and here is the sphere. Okay. Now that's I mean, drawing. If you can draw a circle, you can draw a sphere. Okay, that's the simplistic point of view. Okay, here's the thing. Okay, here is somewhere here, you have got the axis of the thing. Right, fine. So there we are. Okay, and of course the circle, the sphere touches the cone in a circle which will possibly look like this. Okay, I shall make it more precise in a minute. And then, okay, so the center of the circle will be important. So let me just, okay. Right, there we are. Okay, so let me make this circle a little bit more precise. The circle in which the sphere actually touches the cone, so to speak, fits it. Right. Great. There we are. There we are. That's okay. So now, of course, you know, drawing the plane is always almost impossible to make a picture. But you see, actually, there are two planes in this part of the world: the plane containing this circle of tangency, and the plane that intersects the cone. That's what we're interested in. So now, and these two planes intersected in a line which was in the original picture. If you look at it sideways, coming out of the blackboard, perpendicular to the blackboard. So let's assume that we are moving a little bit higher, so looking at the whole thing a little from above, so that the straight line in which the two planes intersect will look perhaps like this. Can you imagine that? This is the plane of the circle intersected with the plane that comes down like this. Of course, this plane, you can't visualize it, and I shall help you visualize it by drawing the curve in which that plane intersects the cone. I shall do that in a minute. But before I do it, let me point out the following thing. So in this straight line, I want you to imagine two planes intersecting like this. So one plane, I don't know. So that's the plane of the circle. And I want you to imagine another plane like this. Okay. I want you to imagine this as well. Okay, so this plane which sort of, okay, so intersects the cone. Okay, so there are two planes. Now, let me intersect this slanted plane that intersects the cone in this interesting curve. So by somehow, okay, so there is a curve. So let me get rid of these things. So there is a curve, something like this. So once again, I'm drawing an ellipse, in fact. Okay, so that's now that's very difficult to get right. Okay, so there is this plane, and there is the other plane containing the circle, containing the red curve, whatever it is. Okay, now, here comes the thing. Okay, now, the sphere. Okay, so let me once again help you visualize the sphere. Now that's a big sphere. And then that big sphere is touched by the plane in a point. Let's call that point F. So there is only one focus in this picture. And now let's take an arbitrary, okay, so that's, let me get rid of this part. Okay. Now let me take an arbitrary point. Okay. Let me take an arbitrary point on my ellipse. So let's call it X, just as in this case. Okay. And, okay, so the apex, let's keep omega. Okay, now if I join X and F, that was blue, wasn't it? Now you know the trick. So if I join x and omega, and if I extend it till this line, x omega intersects the circle of tangency in a point P, I know that the length of xp, which is one tangent line segment to this. Shall we call this sphere sigma? Okay, and shall we call this plane pi, as usual? Okay, right, that's very great. Okay, so this, if I join x and omega, and if I extend it till the point of tangency p with the circle tangency, okay, point of tangency to point of contact with the sphere sigma. Okay, of course, that length, that's this thing, I'm indicating it with one dash, is exactly the same as the length of the line segment xf. I'm indicating it with another dash. That's okay. So far so good. Now I want you to, okay, so let us look at now this at this straight line. Okay, so let me remind you, what's the straight line? The straight line is the straight line in which the plane containing the circle and plane containing the red curve intersect. So I've got in fact two planes. The one plane, okay, so let's call this plane containing the circle pi prime. So there is this pi prime, okay, so horizontal, so to speak, plane, and there is this pi plane which contains this red curve. Good. So by the way, this angle between them, okay, so let's call this line D. Okay, but that's, by the way, is a fixed notation. D. You've got D and F. Good. Now I would like to invite you to observe the following. Okay, so let me join omega with the center of the circle. I don't know what the center, that is not really terribly interesting. Let me join the center to P, that's a right triangle. Let me now drop a perpendicular onto the plane containing the circle. So this is a right angle too. And finally, let me join. Now I need a third color. I don't have a chalk, extra chalk, so I'm sorry. Let me use white. I would like to look at, okay, so this point X is on the red curve, and red curve is in the plane pi, and this straight line D is in the plane pi. So I drop a perpendicular. So I look at the distance. Between the point X. Let me put the designation here, and the straight line D. So let me drop a perpendicular from X onto D, and let me call the foot of the perpendicular X perpendicular. Right. Now, here is yet another observation. I invite you to remember your three-dimensional elementary geometry. You've got a point outside the plane pi prime. You drop a perpendicular. The foot of the perpendicular is, let's say, y. And there is a straight line inside the plane pi prime, and you drop a perpendicular from the very same point onto the straight line. And if you take the foot of the perpendicular drop from the point onto the line to the foot of the perpendicular drop from X to the plane, if you join them, then you will you will obtain a very nice, very beautiful right triangle, another right triangle. And now let's look at these two triangles. So let's call this Y. I invite you to look at the triangles X, Y, P, right triangle, and X, Y, X perpendicular. Observe, check that. What's this angle? Let me call that angle beta. So that's the angle between the axis of the cone and one of the generators. Can you imagine that? Okay, so you've got this cone, okay, the apex and all these generating lines, and there is this axis. You imagine it as a vertical line. And you've got this axis, the axis, and all the generating lines make the same angle with the axis. That's beta. It's a fixed angle. Okay, it's independent of, so it's independent, so you can imagine it, so that's your cone, that's the axis, that's the generator, and that's the angle. Okay, so this beta is independent, so okay, let me point out, independent of the position of x. Wherever you choose x, beta is the same. How about this angle? Okay, so by the way, since this is beta, so is this beta. The angle yxp in the right triangle xyp. Now I invite you to also look at the angle x tilde y. So let me call this alpha. And what is that angle? Well, that angle is exactly the angle between the plane pi prime and pi. So let me do it like this. It's a fixed angle too, it's constant. They're all constant. Now, okay, so there is one simple computation. There is one simple computation which will reveal everything. Now I would like you to şurası mı? So may I draw this picture again? So I would like to draw this picture again. So I've got one right triangle like this. This is a right triangle. That is x, y, x perpendicular. And this angle is alpha. And I've got another right triangle. Do you see? I mean, it's really delightful to do three-dimensional geometry. At every step, you reduce your three-dimensional geometry to 2 dimensions, but you must do it in the correct way. Okay, so this is another right triangle, this P, and this angle is beta. Okay, now, just as in this case, I would like to make a very small, so let me call this the second characterization. And let me do a second characterization. Let me do a simple computation. Characterization. Now, that's what's coming. Okay, so let me do the computation first here. Şunu yapmak istiyorum çocuklar. What I want to do is the following. I want to compare the distance of this point x from the point f to the distance of this point to the line D. Okay, so here's the thing. Here's the thing. I take the distance xf. So the point. So this point, çocuklar bu noktada, so this point is called the focus. Okay? So the distance between the point and the focus, and the distance between the point and the line D. That is equal to, okay, so xf. So to know the distance between a point and a line, all you have to do is to drop, you have to drop a perpendicular from the point onto the line, and you just measure the distance. So x perpendicular, there it is. Şimdi hanımlar beyler. That's your x perpendicular. I know that, okay, so let me conclude. I know that xf, okay, so şuraya yazalım. This is the line, this is the length of the line segment, okay, from the point x until the point of tangency, so xf. Well, I know that it is exactly the same as xp. You know, it's the same thing again, okay, so all line segments have the same length. xf is equal to xp. So instead of xf, I put xp. X perpendicular. Now, my computation is reduced to a computation in this part of the world. You see, xp is simply the length of this thing, xy divided by cosine beta. And what about x perpendicular? Well, it is xy, the same xy, divided by sine alpha. Hanımlar beyler, xy's cancel. I'm left with sine alpha divided by cosine beta, which is of course a constant. Take x anywhere on your curve. Anywhere on your curve. If you measure the distance of x from the fixed point f to the distance between the point x and the straight line d, the ratio of these two lengths is fixed. It's independent of the position of x. Now that is the second characterization, because you see, here is the second characterization. Okay, so I'm just following this same template. A conic section. Here is the thing. A conic section. A conic section with focus f. Okay, so this straight line has a special name, focus f, and that straight line is called directrix, and directrix d, and a third piece of datum, eccentricity. Okay, so focus is one piece of the data that's required. Directrix is yet another thing. And there's a number. It's called eccentricity. And it is traditionally denoted epsilon. Okay, that's a number. That's a number. Is the set. Okay, so let me is the set. Okay, so I'm using exactly the same kind of notation. So it consists of those points x in the plane. So you can, if you like, say x in the plane, the analytical, in the Cartesian plane, if you like, with the following property, that the distance between x and f, x and the focus, divided by the distance between x and the line d, is equal to epsilon, fixed. Well, this is a conic section with focus f, directrix d, and eccentricity epsilon. That's interesting. So let me draw you a picture, final picture. So what you have, in fact, expression like this. So you have a directrix d. You've got a focus f. And you choose a number, epsilon. Now let's assume epsilon is something like a half. Okay? So let's try to choose points which have the following property, that the distance to f divided by distance to the line will be 1 over 2. So something like this, perhaps, huh? Perhaps, huh? Okay, so you can check that if you choose the eccentricity a half, what you will get is going to be something like this. So that's the curve with eccentricity equals a half. Now if you choose eccentricity to be 2, let's say, to the opposite, so that you have to start actually at a point where x, okay, so something like this. xf to xd is 2 to 1, so it's something like this. So perhaps something like this. Perhaps something like this. Yeah, like this, like this. So you will get a curve which will be like this, and there will be a counterpart on the opposite side. I'm not going to do that. So this is what happens if you choose your epsilon to be 2. And if you choose your epsilon to be exactly 1, so you must be looking at those points which is equidistant to the point and to the line. So you start with the midpoint, you go there, you go there, you go there, you go there. Okay, so that's what happens. So that's the critical curve. That's the critical curve with epsilon equals 1. Okay, so terminology. If epsilon is larger than 1, the thing is called a hyperbola. If epsilon is strictly less than 1, it's called an ellipse. And if epsilon is exactly 1, then it's a parabola. Okay, right. So there it is. So these two treatments are equivalent. So these two characterizations are, well, slightly different looking characterizations of the same family of curves. These are conic sections. Now, starting from these two characterizations, we shall go deeper into the geometry of the conic sections next week. So we shall be asking questions like, in which way can they be used in solving problems of geometry, in generalizing things? For instance, it would be for me most interesting question. So ellipse, which contains the circle as the family of ellipses. The family contains the circle as a special case. So in what way the properties of the curve called ellipse are generalizations of which properties of the circle? So this kind of questions I shall be asking and partially answering in my next lecture. And there will be a few results which will be quite peculiar to conic sections themselves. Okay, so